Has it started? Yeah, okay, we start recording now. Okay. All right, so we'll continue. This week's topic is on multiple integral, but well, as you know that we are starting 1 week early for maths, so although it's week 9, but we continue with the topic for week 10, which is the multiple integral, okay? Yeah, okay, so the end of this week, by tomorrow, you should be able to do the following, i.e. to evaluate the double and triple integrals, and also to convert the rectangular coordinates to polar coordinates and cylindrical coordinates, right? So, okay, let's have a quick review on the definite integrals. So if you recall, for previously you are used to function with single variables, okay? So in this case, if you have your y here, then y is a function of fx. So this is y as a function of fx, and your x-axis is the x variable. So this is a single variable. So if you integrate fx with respect to x from the interval a to b, then you would expect to find the area under the curve. So if that is if you you integrate analytically this one, okay? So if you integrate from a to b, the function of x with respect to x, you'll get the area. You can also estimate the area by dividing the interval a to b to subintervals with equal width. So you want to divide the a to b and with n segments, and you know previously we talked about this in applications of integration, where when you divide the intervals into n number of intervals, it will be more accurate as n approaches infinity. The higher number of n, the more accurate your estimation will be. So you can divide this into several rectangles and find out what is the area of each rectangle, and you sum it up, and that will be equal to the analytical form of the integration. Well, you will learn about this approach more during numerical methods in engineering in the next semester. Okay, approximate the integration for some functions which are non-integrable analytically. Right, so that is for single integral or functions with single variable. But now we're going to do for a double integral. So when we do single integral, when we do the integration, we can find out the area. So what can we get when we do double integration? Okay, so let's have a look here instead. So you can also look at your notes. These are the things that is extracted from your notes. Yeah. Okay, so let's consider a function f of two variables defined on a closed rectangle. So you can see at this diagram here. Okay, so you can see that, okay, now you have a function z. So z here is a function of x and y, because in real life, in engineering especially, rarely it is that you have a function of a single variable. A lot of things are a function of many variables. Okay, that's just how life is. For example, if you want to take example in your own life also, the way you react to a problem is a function of several variables. It is not a one-way function of, let's say, how you feel, how you were taught to react in that situation, your upbringing, your belief system, your value system. So those are the multiple variables that affect how you react to a situation. So what I mean to say here is that you need to get used to when we do double integrals and multiple integrals in this case, you need to get used to something, a variable here. Let's say this quantity z is a function of two things, x and y, instead of just y equals to fx, because let's say if you some engineering applications, so if you have a flow in a pipeline, so the flow in the pipeline is a function of different coordinates of the flow, meaning, let's say the density at this point may not be the same with the density in the middle of the pipeline and the density here. So it's not a straightforward function of just one variable. So that's why we need to do the double and triple integral. So but now let's just talk about the mathematics of it without the engineering applications, okay? So suppose you have this function f(x,y). So this function z is a function of variables x and y. So let S be the solid that lies above the R. So this is your R region. So your R region lies on your xy plane. Okay. So the x interval is A to B, and the y interval is from C to D. That will give you this square region here, and your function z is like it lies somewhere, you know, in this area. So the S is the solid that lies above the region R, but under the graph of f. So when you want to integrate this function f of x and y with respect to x and with respect to y, then that will give you the volume. Okay, that will give you the volume. So how we want to approximate this is also the same like when we want to approximate the area of a under the graph. Let's say this is what we see previously, right? So you divide into n subintervals, and then you find out what is the area of each rectangles, and you sum it up. So we are doing basically the same thing in this case for double integrals. So but this time we have different what do you call this, the cubes, okay, the rectangular cubes. So you divide the interval A to B into n number of intervals, and you divide the interval C and D into m number of intervals. So delta x will be equal to b minus a over n, and delta y is then d minus c over m. So n and m are the number of intervals, and it will be more accurate as you reach infinity. The higher number of n and m, the more accurate your approximation will be. So that will give you the volume of each rectangular cubes here. Then you do the same for all the other rectangular cubes at different regions, different intervals, m and n. Then you will end up with this picture here, where you have, you know, how many number of rectangular cubes, and you add all those volumes together to get the volume of the solid S. Okay, this is your solid S, which lies above the R region and below the F function. So that will give you the double Riemann sum of the integral form. So this is your double Riemann sum, this one, in terms of limit. So if you convert that limit into analytical integration form, it will give you this, just this function here. Yes, this form, integral form here. Okay. Yeah, this one. So integral of the region R, f of x and y with respect to the area. So the area is basically the delta x times delta y. Okay, the area of each rectangle here is delta y times delta x. Okay. Any questions so far? You just give me a shout out, because or just put in the chat box. Okay. So well, that is the concept of double integrals, where you can find the volume of the solid that is formed above the region R and below the curve fx. So next is that we want to use iterated integral to actually evaluate the double integral. So in this case, suppose that the function fx is f is a function of two variables. So f is a function of x and y that is integrable. So you can integrate it analytically on the rectangle. So your region AB is your the region for the interval for the x-axis, and CD is the interval for y-axis. So we use the notation integration of fx from C to D with respect to dy to mean that x is held fixed. X is considered a constant, it's not a variable, because now we are integrating the function with respect to the variable y. and fxy is integrated with respect to y from the interval y equals to c until y equals to d. So this procedure is called partial integration with respect to y. So you can compare this with the ones that you learned before about the partial differentiation. So when you do partial differentiation, you just differentiate the function with respect to one variable only. Okay, so if you just differentiate with dy, then you just take the x as constant. So same thing here. So now this is integration. So we do the partial integration with respect to y, and then we integrate the outside of it. So like in this case, let's say you have this integral from a to b, area x dx, and this is your inside area. This is your f of xy dy. So you integrate the inside, then you integrate the outside. So that's why it is called the iterated integral. You do it one by one. But usually the brackets are omitted. We don't really put the brackets. This is just to help you visualize that we are doing the inside first, then only the outside. Okay. So it depends which one you want to integrate first, with respect to y first, then with respect to x, or you can also integrate with respect to x first, and then with respect to y from c to d. So basically, if you have a function fxy, if you put dy inside, then you put the limit of y inside. If you put the dx inside at the bottom here, then you put the limits of x inside and the y outside. Okay, then you just do the integration in the inner part, and then after you got that, you do the integration at the outer part. Any questions so far? No? Right. Question, then we proceed with Fubini's theorem. So Fubini's theorem mentioned that if you have a function f, it is continuous on the rectangle R with this region. Okay, so just let's say this function f, you can define it within these intervals of x and y. And then if you write down the integration, let me use a pointer. Okay, so if you write down the integration, so you integrate the function fxy with respect to dy and dx. So you can break down this double integral into respective intervals. So here you put dy inside first, so you have c and d. Then the dx, you have the a and b as the limit. You look at this region here, okay? So the limit of x is between a and b, and the limit of y is between c and d. So actually this and this side is the same. So doesn't matter if you want to do dy first, then only dx, or you want to do dx first, then only dy, but you just have to be careful with the arrangement of the interval that you put here, because sometimes a function, it is easier to integrate maybe with respect to y instead of to x first. So it depends on the function that is given to you. Okay, so there is also this thing where, let's say if your function fxy can be factored. Okay, so let's say originally your function is in terms of x and y. However, maybe some of the items in the function are repetitive, and you can factor it out, and you can separate them, separate the function in terms of a function of x only and a function of y only, like this. So this fxy, you can separate them into just g of x and h of y. So g is just a function of x, and h is just a function of y. So when you put this inside dx dy, so here in the inner interval dx, hy will be considered as a constant because it doesn't contain anything on y on x. So you can take out this hy to the outside because it's a constant. So you get something like this. So you put the hy here. Okay, so then you just integrate the inside with respect to x, and the function is only in terms of x. But then this hy also, you can take it out altogether. So just take out the interval of integral of hy from c to d with respect to y. So this is only if you can factor out the function f(x,y) into the product of g of x only and h of y only. Okay, so yeah, in short, Fubini's theorem mentioned that if you have this kind of function where there are two separate functions with single variables inside, so you can separate it in advance before you even do the integration. Just be careful with the intervals given. Okay, so let's do example. Okay, so for example 1. So this example is also available in your notes. Okay. So in this case, you want to find the volume of the solid that lies above the square R. So the R intervals is is 0 to 2 and 0 to 2. So the limits for X region, X interval and Y intervals are the same. So this is for X and this is for Y. It's the same. So this one is A and B, and this one is C and D. And below the elliptic paraboloid, so this is your function f x, y, as shown in this figure here. So this figure is obviously taken from your notes. So you can do it. Let's do first integrate with respect to x and then y. And next, if you integrate with respect to y and then x. I know that all the solution is already available in the notes, but well, you need to be able to do it on your own anyway, right? So just let's do it together. Okay. So first with respect to x and then with respect to y. So you can write down your integral is, because the limits are the same from 0 to 2, so you can just write down 0 to 2, and then your function 16 minus x squared minus 2y squared. Now we are doing with respect to x first. Okay, so we put dx and then dy. So when you integrate this part first, so you just put this 0 to 2 inside also. So 16, when you integrate with respect to x, you will get 16x. Then x squared is x cubed over 3. 2y squared is considered a constant here, so 2y squared x. And then you put the interval from x equals to 0 to x equals to 2. I mean, I'm just putting the x's here so that I'm not confused, because we have now inside here we have both y and x, but just to indicate clearly that these are x values. Okay, so then you just put the values in, integrate from 0 to 2. 16 times 2 minus 2 to the power of 3 over 3 minus 2y squared times 2. And since everything is in terms of x, so if x is 0, then everything will just be 0. Okay, so then you evaluate the numbers inside. I think if you look at your notes, you can also see this. Say, okay, now you see that it only comes down to just one variable, which is y here. So you just integrate this 88 over 3 minus 4y squared with respect to y. So you get 88 over 3y minus 4 y cubed over 3. Then you put in the values from y equals to 0 to y equals to 2. Then you get 88 over 3 times 2 minus 4 over 3 times 2 to the power of 3. Then you evaluate the number, minus 0 lah, okay. You get 48. Okay, so this is when you do the integration with respect to x first and then only with respect to y. So you can do the same for integrating with respect to y first, then only with respect to x. So let's do that. Okay, so v equals to integral from 0 to 2, 0 to 2, the function 16 minus x squared minus 2y squared. Now dy dx. So we are going to do the inner integral first. So 16y. So x squared here is considered a constant, so just x squared y. then 2 over 3 y cubed. Now evaluate from y equals to 0 to y equals to 2, then dx, then continue, 16 times 2 minus x squared times 2. Okay, and when you evaluate and simplify the numbers, you get this. Okay, now you are just integrating this function with respect to x. Okay, sorry. 80 over 3x minus 2x cubed over 3. Put in the values from x equals to 0 to x equals to 2. Then you will get 48 also. So you can see that regardless if you integrate dx first then dy or dy first and then dx, you will get the same final answer, which is 48. Okay. So the next example, to evaluate the iterated integral, this function, and the only difference here is just the intervals. Okay. So I guess you can do this on your own anyway, but let's just do it together. So this will be, let me change the color. Okay. Integral from 0 to 3. So now we are integrating the inner one. So x squared y squared over 2 from y equals to 1, oops, to y equals to 2, and then dx. Okay, so you get, I want to continue here. So integrate 0 to 3 and just put in the value of y. Okay. So you get 3 over 2 x cubed over 3. You can delete the 3 from 0 to 3. So you get okay. So well, I hope by now you just, you get the point that, okay, we know when we're given a function here, just integrate the inner integral, and then we integrate with respect to the outer integral. Okay, any question? No? Have you woken up? Right, next is the average value. So the average value is basically if you have a function of f of one variable, so f of x, defined in the interval a and b, so you can get the average value by dividing the integral of fx with respect to x from a to b, and then you divide by the, just b minus a, the interval itself. So in a similar fashion, we can define the average value of a function of two variables. So in this case, now you have f of x and y, and instead of dividing by the interval b and a, now you are dividing by the area of the region R. Okay, so what's the point, or what's the purpose of knowing about this average value? So if you look at your notes, then it says that, okay, why do we have this average value is that, okay, so if you have this function z, so z is a curve, okay, this is your, so you know that this is z, this is x, and this is y, okay, so you have a function, anything, yeah, mountainous region or something, right? So So if you have this function z in the plane of xy and the region is this is your region R here. So okay, your R, and then basically the average value will give you the height, which is the same, the volume as the solid that lies under the graph of f. So meaning here, when you have the graph of x, it may be going above and below the plane, if as you can see here. Okay, it can be going to the negative values of z. Okay, because z obviously doesn't start at the only 0 to positive. It also have the negative value downwards, and same thing with x and y. So if you just chop off the mountainous region here and you put it inside the valleys, okay, you put it inside the empty space that has a downward curve here, and then you can get the same value, the height, such that the height, if you multiply with the region R, you can get the same volume as what you would if you were to do the double integral of x and y with respect to the area here. Do you get what I mean? If you don't understand, please ask question. So quiet. Okay. Yeah, let me see how many people are in already. Oh, we have 60. I thought we were supposed to have 78. But anyway, doesn't matter. They can watch the recorded later. So no questions so far? It's okay. So just bear in mind this average value. Okay. Why do you need to know the average value? Is such that you have to know what would be the height of any other solid that would have the same volume as this function if they were to lie above the region R but with different function of f. Okay. Okay, so now we proceed with double integrals over general region, because previously what we did was, when we are given this axis z, y, and x, so you know that previously we just defined our region as a square or rectangular fashion lah. Okay, from A to B until C to D. So your region R is a square or rectangle depending on the width of the intervals lah. But then we don't always want to integrate this simple from A to B and C to D. Okay, we want to also be able to integrate the function not just over rectangular region but over a region that is of more general shape, any shape. Okay, the region D is of any shape. So there are two types of regions. So previously in the first half of this, in the first half an hour, we just talk about the rectangular region like this. Now we want to be able to do in a more general shape of the region, not just square. So there are two types of regions. Okay, there are type 1 and type 2. So what makes the type 1 and type 2 different is just where the intervals are parallel to. So in type 1 region, x is fixed from A to B, but the intervals as at the y-axis is as a function of x. So this one is, we say that it's type 1 because the intervals are parallel to the y-axis. Okay. Whereas for type 2, the intervals are parallel to x-axis. So in this case, the interval at y is fixed from C to D, but the interval at the x-axis is a function of y, from one curve to the other curve. So here, for type 1 and type 2 regions, if you were to do the double integral for each respective regions, so you would want to settle for the integral that has function first inside, then only you put the integral that only has the numbers outside. Okay, because you don't want to end up with a function at the end of the integration. So similarly for type 2, so since in type 2 the numbers are from C to D, so you put C to D at the outside, so then your dy is at the outside, and then you integrate inside where the intervals are the function of y. Okay, I think examples always make the situation clearer. So let's do an example. So this is also an example taken from your notes. So evaluate this region D. The function x plus 2y is your function fxy or z. So dA is just dy dx or dx dy. So where D is the region bounded by the parabolas y equals to 2x and y equals to 1 plus x squared. So this one, first thing you should be able to first draw the region of integration. So if whenever you are given two functions, so you want to plot it on the graph, you can do any, use anything, Excel for example. Okay, so it's useful to sketch the region. It helps you to visualize and decide if it's a type 1 or type 2 region. So this one is a type 1 or type 2 region. Huh? Is this type 1 or type 2 region?
Type 1.
Yeah, type 1, right? Because you see the limits at the x-axis is between -1 and 1. It's the value. It's a value there. But the limits at the y here is a function of x. Okay, now we want to find the points of intersection to determine the limit of the region. So this values -1 and 1 is not given in the question, but you know you can solve for it by doing the solving simultaneous equation, right? So you put 2x equals to 1 plus x squared, and then you solve for x. Okay, so x squared equals to 1, so x equals to plus minus 1. So you know x equals to -1 is 1, x equals to 1 and is another solution. So you put this, you got this value. And then you get the intersection by putting x equals to -1 into any of this function. Then you get to these points. Okay, right? So then after we have sketched the region and you know the intersection, then we can write the limit of the region. So now you know that the limit of the interval x-axis is from -1 to 1, whereas the limit from for the y-axis is that the lower curve is 2x squared and the upper curve is, the upper curve is 1 plus x squared. So that is your limit. So now the next step is for us to do the integration. Okay. So let's do that integration. So your integration is from -1 to 1, and then from y equals to 2x until y equals to 1 plus x squared. And then you put your function is x plus 2y. Then you integrate with respect to y first, then only with respect to x. Okay, so just continue from -1 to 1, and then you integrate with respect to y, you get xy plus y squared. And then you put here from y equals to 2x until y equals to 1 plus x squared dx. Okay, what's next is that you just continue. So here x, and then the y here you put the upper limit. So upper limit is 1 plus x squared plus y squared, 1 plus x squared. So this is the upper limit minus the lower limit. So x times y is 2x plus 2x squared. Okay, the whole thing. Yeah. So next step is to simplify the expression inside the brackets. Okay. X plus x cubed plus 1 plus 2x squared plus x to the power of 4 minus 2x squared. Ya.
yang kat bracket tu y equal to 2x square.
Kat mana sini?
Yang lower, lower limit. Lower limit kan. Y equal to 2x square.
Y equals to 2x square.
Lower limit.
Ni.
Ha.
Okay. Okay, thank you. Okay, yang ni betul Okay, so you well, this one you need to simplify, and then you can integrate with respect to x, and then you put in the limit. Okay, so when you simplify, I think you will get something like this. Okay, then you integrate. And then you put in the limit from x equals to -1 until x equals to 1. And then, you calculate lah. And then from the answers given in your book, in your notes, you should get 32/15. Okay? All right. Okay, next we go to the properties of double integrals. So we just need to read these properties so that we can make use of it when it's useful. Okay, so first property is that, well, if you have two functions, this one, you can separate it into two different integrals. Okay. Some of these properties actually they are quite straightforward, but it needs to be said so that you can see it. I mean, this all makes sense, right? It's all you know. Like what we did just now. Like if we have this one, actually we are just integrating one by one with respect to x. So it's the same thing actually here in the property number 1. And property number 2 is if you have c as a constant and multiplying the function with respect to a, the area, then you can just take out the c, which also makes sense. I think most of these properties, they are actually the same with the properties of single integral so far. Okay, so for property number 3, if fxy is greater than gxy for all values of x and y in the region D, then the integral of fxy will be greater than the integral of gxy, which also makes sense. Okay, property number 4. So let's say you have a region D, and then you can separate the region D into D1 and D2. So where here D1 and D2 don't overlap except perhaps on their boundaries here. Oops. Okay, they don't overlap except at the boundaries only. So you can just divide the integrals. You can divide the region D into D1 and D2, and thus you can divide the integrals. So first you integrate at region D1 plus the integration at the region D2, because sometimes it's quite difficult to integrate from this part until this part here because of the shape of the curve. So maybe it is more useful for you to divide into 2 regions, or even more than 2 regions are also applicable. Property number 5. If we integrate the constant function fxy equal to 1 over a region D, then we get the area of D, which also, well, it makes sense and it's quite betul lah tu kan, macam okay, straightforward. Okay, property number 6. So if fxy lies between M and capital M for all x and y in the region D, then well, the integral of fxy with respect to the area would be also in the middle of the value of M multiply the area of D and the M multiply with the area of D. So you may not see the point of knowing all these properties until you see the application, and if you notice, oh, these patterns are just like what is being described in the properties here, then you may make use of it lah to do other conclusions. Okay, right. So any questions so far? We proceed to converting to polar coordinates.
And not the
Siapa? Tak ada. Okay. Tak ada soalan? Tak ada Okay. Right, so now we want to do the double integrals in polar coordinates. Okay, so if a region R is circular or some part of circle, a section of a circle, it is easier to describe using polar coordinates, i.e. in terms of R and in terms of theta, instead of using the rectangular coordinates, i.e. in terms of X and Y. So for example, here, if you look at the region, the diagram A here, so your region is a circle. So you know that the equation for a circle is x squared plus y squared equals to 1. So this is a standard equation. 1 is just the the radius from the origin until the edge of the circle. So so if you can define the region R here by defining the limits for R, the small r, the radius is from 0 to 1. So from the origin, the distance is 1. And then for the theta, so you can start, because this is a full circle, so full circle is from 0 to 2 pi. Okay, but if you have a region B here, the right hand side here, so in terms of R and theta, so now the region R is bounded by the two curves. One is x squared plus y squared equals to 1, where the radius is 1, and the second is where the radius is 2. Okay, square root of 4 is 2. Okay, so now R is between 1 and 2. That's why you have this interval. And for theta, because this is not a full circle, it's only half circle, so it's only from 0 to pi. Okay? When we want to convert from rectangular coordinates to polar coordinates, you can draw something like this. Okay, so you have this y and x axis, and then okay, so you have this angle theta from the origin from 0, depending on your shape, if it's a full circle from 0 to 2 pi or 0 to pi. But then if you just have any point in time in the graph here, so you just have theta. So you can define sine theta equal to sine theta is equal to opposite over hypotenuse, so y over r. So that's why you get r sine theta equals to y, this one. So same thing with cos theta also. Cos theta is adjacent x over hypotenuse r. So you get x equal to r cos theta. So that's what you get here. And well, apa nama dia? Pythagoras theorem just give you the hypotenuse equals to the opposite squared plus adjacent squared of the theta. Okay, I mean r squared equals to x squared plus y squared. That's all. Okay, so if we let's say now if we divide the circular region R into sections of a circle, a sector of a circle, we can get polar rectangles. So, well, you know rectangle. So what is a polar rectangle? So here, so when you just take a section of this circle, okay, and take it out here, or in this case, not this diagram, this the diagram below instead. So if you just take out a section of this sector and you magnify here, then you can get this region R, and if you divide, you can get polar rectangles. Here now, the theta is from alpha to beta. So your theta is from alpha to beta. And your R, the radius is from R equals to A. So here, this is the distance is A. And here, the distance is B. So that's why your R is between A and B. So those are the limits of your region. And then if you divide the interval A and B into M subintervals. Basically, we are doing exactly what we did with the rectangular region R previously. So we divide into equal width of delta R. Okay, so you know that R is between A and B. So when you divide the A and B into subintervals, M subintervals of equal width, then you get the delta R equals to B minus A over M, and it would be more accurate as M is becomes bigger. You can also do the same when you divide the interval alpha and beta, the theta, okay, the theta, the angle. So you can get the delta theta equals to beta minus alpha divided by n, because you're dividing it into the n subintervals. Now the center of the polar subrectangle is, okay, so you just take this subrectangle here, okay, but it is not a proper rectangle. It is called polar rectangles or polar subrectangles because it is still a curved side there, okay. It's not just a rectangle. So the center of the polar rectangle Rij, R must lie between okay, so this is your R equals to Ri minus 1, and this is Ri. So R lies between Ri minus 1 and Ri. So you can get this, the average of this. So Ri star equals to 1 over 2 Ri minus 1 plus Ri. It's just the average of the R. And the theta is between, so here is your Ij minus 1, theta j minus 1, here is your theta j. So theta here just lie between theta j minus 1 and theta j, so that's why you get this. Theta j star is just the average of the theta. Okay. Then the area of a sector of a circle of radius r and central angle is, you already know this in your previously, 1 over 2 r squared theta for any area of the sector of a circle. Then the polar rectangle Rij has the central angle of this, and thus the area of Rij delta Ai is, okay, the area of this, okay, is this area minus this area. And then when you factorize the delta theta out, you just get Ri squared minus Ri minus 1 squared. And this one you can factorize because A squared minus B squared equals to A plus B times A minus B. So that is what happened here. So you have Ri plus Ri minus 1 and Ri minus Ri minus 1, and just bring the delta theta down. And previously you know that this Ri plus Ri minus 1 divided by 2 is the central of the average of the R. So here the point is to get to the fact that delta Ai, area of the delta area, this polar subrectangle, delta Ai equals to Ri star times delta R times delta theta, because this here is your delta R and here is delta theta. Okay, so yeah, the point is to derive this. Okay. So here in this case, at the end of the day, when you add up all the areas together, you just put it in summation function from I equals to 1 until I equals to m for the R, and then j equals to 1 until j equals to n for the theta, and then the delta AI. So now instead of fxy, now your function is in terms of r cos x and in terms of r sin x, because we want to convert from rectangular coordinates to polar coordinates. So then, because this delta AI is equal to Ri star times delta R times delta theta, so that's why you get this term here. Okay, are you following? I hope you can follow. If not, please ask. Well, we are still in the same domain of the area of region R in polar rectangles. In this case, it's just that if you write RF because previously we have this r and you have this f. Okay, so if you combine the r times f, the function of f, into just g of r and theta, then you can write down the function is like this. You just convert the Riemann sum for double integral from this to this and put it in terms of analytical integral from a to b and from alpha to beta respectively dr theta. Okay, so to cut things short, if you have integral about the region R for f, x and y at the area of the region R, and you convert x and y into r cos theta and r sin theta, so then you also change the limit from a to b to alpha and beta instead of x equals to y and y equals to 1. Okay, because now everything is in terms of r and theta, but here the dA, don't forget about the dA. dA is equals to dr d theta, because previously dA is equals to dx dy or dy dx. But when you put it in terms of polar rectangles, dA is equal to r d theta, r dr d theta, not just dr d theta. Okay, so this is where it gives some emphasis here. So just imagine your polar rectangle. So here, I mean, the length here is r d theta, the length here is dr. So your area is r d theta times dr, not just dr d theta. Okay, so just pay attention to this. So yeah, I cannot say this enough with enough emphasis. dA equals to r dr d theta, not just dr d theta. Okay. Right, so let's do example. After this, we're going to have a break. So let's just finish up with this example 4. So evaluate the integral at the region R. This is your function 3x plus 4y squared dA, where R is the region in the upper half plane bounded by the circles x squared plus y squared equals to 1 and x squared plus y squared equals to 2. So first, we sketch the region. Always sketch a region. Helps to see the boundaries. And then we describe the region R as in terms of x and y. Okay, now your y is just greater than 0 because everything lies on the positive side of the y-axis. Nothing lies at the below here. So you can just put your interval y is y greater than 0. And your x squared plus y squared is actually your r because, well, previously we've seen this, right? So actually r squared lies between 1 and 4. So your r is between 1 and 2 at the positive side only. Okay, so the in polar coordinates is given by r is lying between 1 and 2 and theta is from 0 until pi because it's a semicircle. Now we want to convert the x and y into polar coordinates and also dA equals to, so because this is dA, so here dA is equal to r dr d theta. And then we can do the integration. Okay, so let's do that. Oops. Okay. Okay, so yeah, let's do this example. So we want to integrate the region R, 3x plus 4y dA. So x is r cos theta, y is r sin theta, and dA is r dr d theta. Okay, so you know that r is between 1 and 2 and theta is between 0 and pi. So this you can write down as we put the 0 and pi outside and then we put the r inside from 1 to 2 and 3x, x is r cos theta, so 3 times r cos theta plus 4y, y is r sin theta, so 4 times r sin theta, and dA is r dr d theta. Okay, so here you can see, oh sorry, 3x plus 4y squared Is it squared?
Yes.
Okay. So this thing here is squared lah. So just put 4r squared sine squared theta. Macam tu. Okay. Then because you have this r here, so you want to put it inside the interval. So you just put here r squared. And here you have r cubed. So 4r cubed sine squared theta dr d theta. Okay. And then you integrate the inside first, then you integrate the outside. So 3r cos theta d theta. Now this cos theta, everything we treat it as a what? Constant. Okay. So 3r cubed over 3 cos theta plus 4r 4 to the 4 sine squared theta. So from r equals to 1 until r equals to 2, d theta. So r minus just cos theta plus sine squared theta d theta. Apa? What did you get?
7 cos theta.
7 cos theta plus 15 sine squared theta d theta. Now you need to integrate the cos and sine theta. So here you may need to use some trigonometric identity. Okay, so which one do you want to use? Well, okay, let's use this one. Sine squared theta equals to y minus cos 2 theta over 2. So you put this inside this. Okay. Yes, continue 0 to pi 7 cos theta plus 15 over 2 times 1 minus cos 2 theta d theta. Then you integrate lah with respect to theta and you put the limit. So 7 sine theta plus 15 over 2 theta minus 15 over 2 divided by 2 sine 2 theta. Put the value from theta equals to 0 until theta equals to pi. Okay, then you put in the values. Okay, 7 sine pi minus 15 over 2 pi minus 15 over 4 sine 2 pi minus 7 sine 0 plus 15 over 2 times 0 minus 15 over 4 sine 0. Okay, so sine pi 0 plus 15 over 2 pi minus 0 minus 0 minus 0 plus 0. So 15 over 2 pi. Got it? Okay. So just follow the steps, okay? First of all, identify the limit of r, identify the limit of theta, and then x is r cos theta, put it inside. Y is r sin theta, also put it inside, and then dA is r d theta, and be careful and just proceed with the integration. Okay, so let's have a quick break before we continue with a triple integral. Any questions before that? I need to take the attendees list. Any questions? Tak ada? Okay, take a 5 minutes. Is it enough? 5 minutes? Take 5 minutes break and then we'll come back and continue. Okay? All right. Are you guys back? Hello.
Yes.
Okay, good. Okay, let's continue. Okay. Right. Yeah, I missed this before going to the break. So we did example 4 just now, and we can also apply polar coordinates for more complicated regions, just like what we did in previously in the rectangular coordinates for general region D, because we don't necessarily work with when we work in the rectangular coordinate, a rectangular region. A to B and C to D, then we can define the region D in terms of a more general shape. We can do so too with polar rectangles, because we don't always work with these nicely bounded curves from r equals to something to r equals to something, but sometimes we need to work with this kind of curve instead. Okay, so in this case you have this bounded region from r equals to h1 as a function of theta until r equals to h2 as a function of theta, and the theta is from alpha to beta. Okay, so this is a more general region of polar coordinates. So, well, but basically it's the same thing, okay? So similarly with the region D, where you define the limits from, let's say you integrate with respect to x first, and then your lower limit is x equals to h1 as a function of y, and the upper limit is x equals to h2 as a function of y, then we can do the same for polar coordinates as well, where let's say we want to integrate with respect to r, but now r, the lower limit is this is supposed to be in theta lah, okay? So r is r1, I mean the lower limit is r equals to h1 and upper limit is r equals to h2. Okay, so from here we get the same thing basically. dA is still r dr d theta, x is r cos theta, y is r sin theta, so just changing the limit in terms of a function of theta. Okay, so this is just a simple formula where you just have a function of 1. So if you just have function of 1, then it's just a constant. So dA is just r dr d theta, and in this particular example, the r starts from 0 until r equals to h as a function of theta. So first, you just integrate with respect to r. So you get r squared over 2, and then you put in r equals to 0 until r equals to h theta. Then eventually you will get 1 over 2 times h theta, the whole thing squared, and you integrate this with respect to theta if you know what is h as a function of theta. But the example stops here, so thank God. So we just need to stop there. But in case you need to use it in future, you know where to find this from. Okay. Let's continue with triple integrals. So if double integral is a function of 2 variables, then obviously triple integrals is a function of 3 variables instead. So f here is defined on a rectangular box. Okay, so B is for box. So the interval x, y, and z. So x lies from A to B, y from C to D, and z from R to S, for example. Okay, so you can follow the same methodology where you divide the box B into sub-boxes. Okay, previously if you have a region R, you divide them into sub-rectangles, and then you get some rectangular cubes. So now you do the same. So you divide B into sub-boxes. So each sub-box, you have a volume of, okay, so each sub-box, the length, width, and height are given here in terms of delta x, delta y, and delta z respectively. So the volume is just delta x times delta y times delta z. Then you can form the triple Riemann sum like this. So where you just sum up all the volume of each cube, okay? So by analogy with the definition of a double integral, you can define the triple integral as the limit of the triple Riemann sum. So from the limit notation, you can convert it into the analytical integration notation. So just integrate the box B, the function of x, y, and z, dv. So where dv is dx, dy, dz. Okay, so if f is continuous on the rectangular box B with the region given A, B, C, D, and Rs for x, y, and z respectively, then you just integrate the function f or as a function of x, y, and z, first with respect to dx, A to B, with respect to y, C to D, and with respect to z, r to s, and you can of course interchange the order of the integration. So in this case, you have more permutation, more different orders of arrangement. So you can do dx dz dy, dy dx dz, or dy dz dx, and anything. You have a lot more probability to play around with to do the integration. But regardless, you should get the same value. Okay. So the iterated integrals on the right side of Fubini's theorem means that we integrate first with respect to x. Well, basically it's the same steps like what we did in double integral. So there are 5 possible orders like I mentioned previously. Okay. Now let's just do the example. To evaluate this triple integral, the box B xyz squared with respect to, the volume dV. So B is the rectangular box given by the limits, the intervals for x, for y, and for z. So okay, let's just do this quickly. Oops. Okay, let's just do this. So you want to integrate B x y z squared dV. So we put the z outside. Then inside is the y, so y is from -1 to 2, and z, x is from 0 to 1, and put the function xyz squared, so dx, dy, dz. Okay, so 0 to 3 and -1 to 2, so x squared, y and z squared are just constant from 0 to 1, dy, dz. So you get from 0 to 3, -1 to 2, y, z squared. Am I doing the right thing here? Yeah? Okay. dy, dz. Okay, so you continue to integrate the inside. With respect to y, you get y squared over 2 times 2 are 4 z squared from -1 to 2 dz, and then integrate, and then you just put in the value of 2 and 1 inside and calculate. You get 3 over 4 z squared dz. Then you get z cubed over 3 from 0 to 3. So you get 27 over 4. Okay? So just the same thing like what we did in double integral, but now we have another variable. So what can we get when we do triple integral? Because when we do double integral, we get the volume. So what will triple integral give us? What do you think triple integral will give us? If double integral already gives us volume, so what's the purpose of doing triple integral? Any guess? Huh? So quiet. No guesses? Well, I'll answer you when we get to the example later. Okay. So that is if we do triple integral over a box. So this is easy because your region is defined by a box, A to B, C and to D, and R to S, just like what we did in this example 5 here. But life is not always easy, so we need to do triple integrals over a general region. Okay, so let's define the triple integral over a general bounded region. So in any shape, we want to be able to do any integrals, double or triple, in any shape that is given to us. Okay, so in this case, we restrict our attention to continuous functions f and to certain simple type of regions only. Okay, we don't deal with discontinuous functions, the ones with no convergence, those things we don't want to deal with it for now. Okay, so there are different types, type 1, type 2, type 3. So type 1 region, this solid region E is said to be type 1 if, okay, just look where the shadow of the solid lies in which plane. Okay, so in this case, your region E, the shape of the the shadow lies on the plane of X and Y. So this is type 1 because the shadow lies on the plane, XY plane. Okay, and in this case, the limit from Z1 until Z2, i.e. the lower and upper limit of Z, is defined as a function of X and Y. Okay, yeah, so this is type 1 region. Type 2, okay, type 1 plane region has two types. Okay, we have type 1 region, but type 1 region also have two types. This is type 1 plane region in the type 1 setting. Okay, how do I put this into context? Okay, here you have this solid E, and you look at the intervals for x-axis is A and B. Okay, A and B, whereas for the y-axis is defined from y1, y equals to g1 of x and y equals to g2 of x as the lower and upper limit. Okay, and for z limit is from u1 as a function of x and y and u2 as a function of x and y. So this is type 1 particular example 1. So x is given by a number, limit of y is a function of x, limit of z is a function of x and y. So you want to put the limit of x at the outermost side of the integrals. Okay, put a and b at the outside and dx at the outermost. And then put dy in the middle because it's only a function of one variable, and put the one with the most variable inside dz. Okay, because z is a function of x, y, and z. So you put it inside. Okay, next is type 1 plane region, example 2. How is it different from type 1 plane region, example 1? So in this case, you look at this limit of y is from C to D. Okay, now the limit is C to D at Y. So that's why it's still a type 1 plane region because the shadow of the solid still lies on the XY plane, but this time the Y limit is a number from C to D. But whereas X, limit of X is a function of Y. So X lower and upper limit is defined by H1 and H2 as a function of Y respectively. And still the limit of z is a function of both x and y. So in this case, you put the outermost integral c and d. So you put dy at the outermost integral, and then you put dx in the middle because it's a function of only one variable, and you put dz inside because it is a function of two variables, or maybe three, x, y, and z. Okay. And there's this type 2 plane region. So just look at where the reflection or the shadow of the solid. So now the shadow is on the YZ plane. Okay. So here it's type 2. So, well, it's the same thing lah, basically, you know, like you just need to identify what are the limits for the Z axis, the Y axis, and the X axis, and you put which one is the easiest, you put outside, and the one with just one variable, you put in the middle, and the one with the most variable, you put in the inner side. So in this case, X is the innermost integral because X is the function of Y and Z. Okay. Then type 3 is where the shadow lies on the XZ plane, okay, in this plane. Okay, so it's basically all of triple integrals. It's just that where the shadow lies will define the order of integration, the easiest order of integration. You can, of course, do any order, but then you also want to make your life easier. So in this case, you want to put dy inside and then the dA outside. dA is dz, dx, depending on which one you decide on your own when you are given the problem later, which one you want to do. Okay, but in this case, seems like the y is the most, the simplest one. So no, sorry. Y is the most complicated one, so you put it inside. Okay. So type 1, type 2, type 3 depends on which plane the shadow of the solid lies at. Yeah, please, if any question, just let me know, okay? Right, next is if previously we convert the for double integrals, we convert the rectangular coordinates into polar coordinates, but for triple integral, we convert it into cylindrical coordinate system, okay, because it's now a function of 3 variables instead of just 2 variables. So let's say you have this point P in a 3-dimensional space represented by the triple integral. So this is okay, this is your distance r from the origin, and then this is the height from the xy plane. The distance from the xy plane is z. So your coordinate of this point P is r, theta, and z. So r and theta are the polar coordinates of the projection P onto the xy plane, like what we did before, where we already know if you're given this theta, then is this is x, this is y, then this is r. So you know that x equals to r cos theta and y equals to r sin theta. So you use the same thing, x equals to r cos theta and y equals to r sin theta, but now z is just z because z is actually just the distance from the xy plane to the any point of the z axis. So there's no need in changing it into r or theta. Okay, so if you need to convert from rectangular to cylindrical, yeah, I mean, this all applies as well, okay? R equals to x squared plus y squared, and tangent theta equals to y over x, and z equals to z. This all applies when you need to convert things from one coordinate system to the other. So for example 6 is to just familiarize you with the cylindrical coordinate system with the rectangular coordinate system. So now you're given a point where the cylindrical coordinate is r equals to 2, theta is 2 pi over 3, and z is z. So let's find the rectangular coordinates in terms of x, y, and z. So how do you do that? So just, well, x equals to what in terms of r and theta?
R cos theta.
R cos theta. And y equals to r
Sin theta.
sin theta, and z is just z. Right? Okay, so now your r is 2, so x equals to r cos theta, so r is 2. Theta is 2 pi over 3, so cos of 2 pi over 3. Okay, and that will give you 2 times 1 over 2, and that will give you -1. Y equals to r sin theta, r is 2, sine of 2 pi over 3. So y equals to 2 times sec 3 over 2. So y equals to 2 and z equals to just 1. So your rectangular coordinate is then x is -1, y is 2, and z is 1. Betul ke? Y is sec 3 lah. Okay. 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 Now, what if we need to evaluate, or it's easier for us to evaluate triple integrals with cylindrical coordinate? Okay, suppose that this solid E is the type 1 region. So the type 1 region is where the shadow lies on the xy plane, whose projection D onto the xy plane is conveniently described in polar coordinates. In particular, suppose that F is continuous and E is a function of x, y, and z. So xy is bounded by the region, xy plane, and z is bounded by the u1 and u2 functions. So u1 is a function as a function of x and y, u2 as a function of x and y. So D is your polar coordinates. So for type 1 region, you know this, okay? You know this already. For type 1 region, And then to evaluate the triple integrals in polar coordinates, so you just put it in the simpler order of integration. So in this case, you put the d theta outside. So you have alpha and beta, and then you put the r in terms of theta, h1 and h2, and then you put the z in terms of r cos theta and r sin theta inside. Okay, if in double integral, we have dA equals to r dr d theta. But now for triple integral, okay, so just imagine your cylindrical coordinates, and now previously if you cut the cylinder, if you cut the polar coordinates, you get polar rectangles. Now you get this, what do you call this? I don't know, polar cylindrical, polar cylinder, polar cube, whatever. But then if you cut the section as a solid, then you get this shape. So here the distance, the length of this curve is r d theta, and the height of this is dz, and the length of the width of this is dr. So the volume of this section is r dz dr d theta. Okay, so you still have the r inside for the dv. So dv is r dz dr d theta in whatever order it is, but as long as you have the r inside, I mean outside. Okay, so let's do example 7. So this is where you can see why we need to do triple integral instead of just sticking with double integral. So if double integral, you can calculate the volume, but for triple integral, you can calculate the mass, because assuming that this is your solid, okay, this is your solid, given solid here. Let's say that, okay, in this case, it says the density at any point of the solid is proportional to its distance from the axis of the cylinder, meaning the density is not uniform and constant. The density is as a function of x and y, okay? Is proportional to the distance from the axis of the cylinder. So that's why we can make use of the function of density. So density is a function of x and y, and then we can do the triple integral to find the mass of the solid E instead of just volume. So if we use the double integral, even triple integral can also find the volume, but the triple integral has an advantage of making us able to calculate the mass of a solid given the density function. Okay, not just density and mass lah. Actually, a lot of things in this world are as a function of a lot of variables. For example, temperature profile across the equipment, across a particular solid. It depends on the amount of heat supplied and the distance between the source of heat and the axis or x and y plane in the solid. So a lot of things, a lot of application, but now we are just focusing on the mathematical aspects of the multiple integral. Okay, not to bother you with a lot of not yet encountered engineering applications. Okay, but so now let's just put back our focus on example 7. So this solid E lies within the cylinder x squared plus y squared equal to 1, below the plane z equals to 4, and above the paraboloid z equals to 1 minus x squared minus y squared. The density at any point is proportional to its distance from the axis of the cylinder. Find the mass of E. Okay, so below the plane z equals to 4. So z starts from 0. So now it stops until 4. So this is your the top of the cylinder. Okay, this is the top of your solid, the limit of your solid. And also this solid lies above the paraboloid 1 minus x squared minus y squared. So this is your paraboloid. Okay, so x squared plus y squared is r. Okay, so r squared equals to, okay, so 1 minus x squared minus y squared is basically 1 minus, and then 1 minus r squared. So this is your z in terms of r. Okay, and the region. Okay, now since this solid E lies above the x-axis, so it's just a half circle. So theta lies between 0, no, it's not half circle, sorry, it's 2 pi. It's the whole circle here, okay? 0 and 2 pi. And then R is between 0 and 1, because this. So R is 1. And then Z is because Z lies above the paraboloid, so the lower limit of the solid is 1 minus R squared, and the upper limit of Z is just 4 because this is the maximum level of Z. Okay, so we have defined the region of the cylindrical coordinates in terms of R, theta, and Z. So now we need to make use of the density. Okay, so density is proportional to the distance from the z-axis. So density is proportional to r, the radius. Okay, so then you can put the density equals to kr, where k is the proportionality constant. So if you can write this density as a function of x and y, or just as a function of r. So k is the proportionality constant. Okay, so now let's do the integration. You've seen this in your notes, but let's go through the steps. Okay. So your function f of x, y, z equals to k. Okay, so now you want to find the mass. Mass equals to the triple integral of the solid E, k times the distance is r, dv, but you want to convert it into polar coordinates. Okay, so from 0 to 2 pi, and from 0 to 1, and from z equals to 1 minus r squared until z equals to 4. Your function is kr. This order is in no particular order. Okay, I'm just putting it here. Okay, and then the r. Okay, now be careful of the order of the integration since this is z. So we put z, and then that is the r, and the outermost is d theta. Okay, so now we just need to do the integration. So kr times r is, you can just put it as kr squared. Okay, so now we do the integration lah. 0 to 2 pi, 0 to 1. So you integrate kr squared with respect to z, you will get kr squared z. Okay, just from z equals to 1 minus r squared until z equals to 4 dr d theta. So kr squared times 4 minus kr squared times 1 minus r squared. Okay. So you can take out the r squared and then kr squared, and then you get, what is it that you get? I think from here you can do it on your own, but let's just continue since we have time. And please spot if I make any mistake. Oh, okay. Here, if you notice, this is a function of r only, and then dr and d theta. So meaning you can take out just the d theta here and just put 1 as a, nothing lah, but not 0. Then you can just put 0 to 1, dr squared plus r4. You remember the Fubini's theorem where you can separate the function because it is one function can be in terms of just one variable and another is in terms of just one variable. So you can separate this into two parts. But you don't have to do that, but if you want, you can. This. Then okay. Then you just evaluate, put in the numbers, everything. So here you have 2 pi k times 1 plus 1 over 5 equal to 12 pi k over 5. Okay? Yeah. Well, I accidentally finished all lectures which were supposed to be in 2 days actually. Normally I finish this 45 slides in 2 separate classes, 2 hours and 1 hour, but now we managed to do it in 2 hours because there are no questions. So I just proceed and finish everything. So are there any questions about the test or anything? Because the next test is testing on week 8, 9, 10, i.e. week 7, 8, 9, meaning integration, application of integration, and multiple integrals. So you can ask now. Is the K necessary? What do you think? Well, because here in this example, it doesn't give you the actual exact function of the density. It just say that the density at any point is proportional to its distance. So whenever something is proportional to something, you would write this down first, right? Rho is proportional to r. R is the distance from the axis of the cylinder. So this is what you are given. Rho is proportional to r. So you need to put it in equal sign. So when you put the equal sign, you need to have the proportionality constant, but we don't know what is that proportionality constant, so we just put K. It could be any other letter though, whatever. Yeah, so answering to your question, K is necessary. Okay, any other question? So I just recap. Okay, I recap. So from the learning outcomes, you should be able to do this. So do you think you can do this? Evaluate double and triple integrals and convert the rectangular coordinates to polar and cylindrical coordinates. Okay, no answer also. Anyway, so just for the test, well, first of all, sketch the region. Just follow the steps here. If you're given any region, give any question, because sometimes you're not given the region. Okay. Sometimes in the example or just go through some exercises. I'm not sure about your tutorials, but maybe you could have been given just the functions, but then you need to sketch the region on your own. So how do you sketch the region if you're not given this diagram here? How do you plan to sketch the region? In this case, you're given y equals to 2x squared and y equals to 1 plus x squared. So let's say in the test you're not given the region. How you're supposed to draw this region? How do you plan to do this? Any ideas?
Use Desmos.
Apa tu? Desmos. This one. Graphing calculator. Yeah, this is a smart way of drawing the region of integration. So you can straight away go to, is it this one? Nah. Okay, so what do you put here?
2x squared.
2x squared. And how do we add another one? 1
Plus x squared.
So you can see there. Macam itulah. So this is a quick way to help you to sketch the region, to help you visualize, you know, the limits. Because if you're just given this question, this statement only, okay, without the x intervals and whether which one is at the lower bound or upper bound curve, then you need to do this, okay? You need to know. All right. Any other question? Ada ke? So everyone understood everything. So what do we do tomorrow? Or then we don't have to have any classes tomorrow lah. I'm going to stop recording.